and this is my video lab report for Physics 2212 Lab 3. This lab investigates the magnetic field of a bar magnet. I'll first introduce some key ideas, important formulas, and go over my setup for the lab. I'll then show you my experimental data calculations, data processing, and observations. After that, I'll introduce my computational model and take a look at my program's output. Finally, I'll go over the results and answer the key questions about the lab. As for key ideas in the lab, you need to understand that a bar magnet is a magnetic dipole and will be treated as such in this lab. Therefore, you need to know that the magnetic field of a magnetic dipole on its axis, as well as know that the magnetic fields can be superposed. This will be important as we will correct some results by removing the interference from the Earth's magnetic field. Another key idea in this lab is computational modeling and writing code to visualize a magnetic field. And lastly, we will need to know how to linearize data for this lab. The formulas relevant to this lab are shown below. The first two formulas describe the magnitude of the magnetic field due to a magnetic dipole, something which will be important in calculating mu, the magnetic dipole moment of the bar magnet. The third equation has to do with the linearization of our data and will be applied in this lab. The last equation defines approximately the magnetic field of a dipole at any location, something we'll use in the computational model. Here's a look at the setup. On the left, we essentially measured the distance for different bx's and plotted this data, as we'll see in just a moment. On the right, we found the perpendicular distance needed for the magnitude of the magnetic field to be 100 microteslas, and then calculated the net magnetic field at the location shown in the diagram, which will later be compared to the results from the computational model. Here's a look at my experimental data, where I have my raw data as well as my graph of ln bx versus ln r. At the bottom, I have my net magnetic field at a location 45 degrees off axis from the dipole. Let's not use this data to perform some calculations. Here I set the first two equations on the left side equal to each other in order to find a symbolic solution for mu circled to the right. I then pull data from my graph as shown in these calculations. Specifically, n is the slope of the graph and ln k is its y-intercept. I got negative 2.95 for n, and k's value is shown on the left. Using these numbers, I solve for mu and 3.206 newton meters per Tesla. Of the observations shown here, only the first and fourth statements describe what I saw in my experiment. I noticed that when the magnetometer was far away from the magnet, Bx was close to zero, and when it was brought closer to Bx increased as expected. The first thing I did was define a function for calculating the magnetic field due to a dipole with a given magnetic dipole moment and a specified observation location. I used the formula I mentioned earlier, shown here again for reference. I then set the locations for 6 of the 7 points where I'd be visualizing the magnetic field. 2 of these points were on the dipole axis, while the other 4 are perpendicular to the dipole axis. After that, I drew arrows for each of those 6 points as shown in the code here, and finally I did the same but for an observation location at a 45-degree angle off axis from the dipole axis. Here's the final result, which shows the two on-axis magnetic fields in orange, the 4 perpendicular magnetic fields in light blue, and a 145-degree off-axis magnetic field in purple. You can see the arrows are scaled proportionally to the magnitude of the magnetic field they represent. Comparing the value from the computational model with the direct measurement value, we can see that the two values are not exactly the same. However, given the various uncertainties and errors in measurement, the two values are accurate to the same power of -5. Therefore, we could say that our experiment was fairly successful in our calculations. Finally, to answer the questions below, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out the meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? Our results for Bx would all have been off by a specific amount due to interference by the Earth's magnetic field. Not only this, but since the magnetic field superposed this would have affected the magnitude of the magnetic field in the second part, leading to inaccurate results. Now with the second question, what if you were to stick two identical magnets together end to end and run the experiment again? How do you expect your measurements to differ? I would expect the measurements to all be multiplied by some scalar constant. I would expect relatively the same results but with different numbers because everything would be the same except for the magnetic dipole moment. Thank you for watching.